start the meeting. Hello, everyone, and welcome to this very special talk of Professor Jan Akyildiz about 6G and beyond, the future of wireless communications systems. But before giving the floor to Professor Jan, let me introduce myself. I am Bujar Krasniqi, Associate Professor at University of Prishtina, Faculty of Electrical and Computer Engineering, Department of Telecommunications. I heard about Professor Jan for the first time back in 2010, when I participated in a plenary featured talk of Professor Jan during the Globcom 2010 conference in Miami, as a PhD student from Vienna University of Technology. The title of presentation was Nano Networks, a New Frontier in Communication. During that presentation, I was impressed to hear about molecular communication, terahertz communication, and nanotechnology. But these keywords are actual still today. I missed the opportunity to have a conversation with Professor Jan at that time, and it took me almost 8 years to have this opportunity again during the BalkanCon 2018 conference in Podgorica. Professor Jan, together with Professor Akyildiz, are working hard to give the Balkan countries a prestigious conference in field of telecommunication named BalkanCon. BalkanCon began in 2017 in Tirana, after that in 2018 in Podgorica, and the last one was organized in Skopje in 2019. In the conversation I had with Professor Jan in 2019, he agreed in principle that after Novi Sad, the next BalkanCon to be organized in Prishtina. But the pandemic situation at the moment made it impossible. On behalf of University of Prishtina, especially of the Dean of Faculty of Electrical and Computer Engineering, Professor Isaac Shaboni, I would like to thank the academic staff and students of the University of Prishtina, local and regional telecommunication companies, colleagues from Polytechnic University of Tirana, University of Montenegro, and other research institutions from Europe for accepting the invitation to participate in this talk. To keep Professor Jan's presentation in time, about 60 minutes, please send your question in Zoom chat, and Professor Jan will answer them only after finishing his presentation. Professor Jan, thank you very much for accepting our invitation, and the floor is yours.
Okay, good afternoon, and thanks for your participation to my presentation. I was very happy when Bujar asked me, or Bujar asked me to give a speech, and Balkan countries are a special place in my life, although none of my roots are from Balkan countries, because I was going to school in Austria and Germany, and I passed through E5 many times. I almost died in Niš in 1977. A bus hit our car on the left side because my girlfriend was driving and I was sleeping in the back of a Diane. So I almost died in Yugoslavia, but anyhow, so I was in many times there, and I really enjoy the people, the culture, and all that. So I'm also very happy that we started this BalkanCon, and last year it's supposed to be Novi Sad, and now we have this year in Novi Sad. So we'll see. So, but our objective is continue to foster this communication between these Balkan countries. So today I will talk about, I did not know that Bujar was in Miami listening to my presentation that time. And so today we'll talk about 6G and beyond. Even the 7G is there, so you may be surprised about it. So I will start with this big picture between the 5G and 6G differences. And as you see here, there is this paper that we took us to 1.5 to 2 years to finish. And with my PhD students, both are finished now, and they're leaving now. So what we try to show is that in terms of peak spectral efficiency, 5G has 30 bits per second per hertz, and we are trying to double it to 60 bits per second per hertz. And peak data rates, we are talking about from 20 gigabit per second up to 1 terabit per second. And then in end-to-end latency, that's one of the biggest problems in 5G. trying to reach 1 millisecond. We are far away from that. Maybe some of the operators know about it. And now we are talking about going down to 0.1 millisecond in terms of end-to-end latency. And the mobility from 500 to 1,000 plus kilometers per hour. And the cell edge data rate, when you're far away from these base stations, currently the expectation is 0.1. Now we are hoping that we will reach 1 gigabit per second, and reliability should be jumped from 10 to the minus 5 to 10 to the minus 9. As you see here, we have very, very challenging objectives to jump from the 5G to 6G. It's really a revolutionary step. And there was a lot of research the last 10 years, moving from 4G, you see this inside, to the 5G. Now we are talking about 6G, right? In the meantime, there are, I don't know, tens of papers. Everybody writes a paper on 6G. So we try to be different, of course, so that we'll cover more bases. So our paper has many more directions than the other ones. And so in our view that we believe that the terahertz, the higher frequency bands, like millimeter wave bands, dictated some of the 5G developments. And now this terahertz band, like sub-gigahertz, sub-terahertz or terahertz, will play a major role in 6G. And then there is so-called reconfigurable intelligent surfaces. They will also boost these performances that I show you, these objectives. And then there are, I call them Internet of Space, things like the CubeSats. So I will cover these three green areas. And then there are some other research directions that we have covered in the paper, but I cannot cover all of them due to the time constraints, like the hardware design for reconfigurable front ends, meaning the transceivers and the antennas. They will be adaptively moving from the lower frequency bands all the way to high terahertz bands. So these are called reconfigurable front ends. It goes with these dynamic spectrum sharing, right? That means no more compartmentalized spectrum bands. So everything will be available to us, whatever is available geographically, timely, spatial, temporal. Then the front end should be able to lock in there and then communicate. So that's really an interesting topic. There is a €100 million investment in the US on this topic. And some of these ideas I will explain in the CubeSats research that we have. And then, of course, everybody is crazy after machine learning and artificial intelligence. And, majority of the people, again, they follow the old fashion of, for example, neural networks or deep neural networks, and keep writing papers, because it's buzzword now. So I really suggest that we should set ourselves back a little bit and, come up with different approaches. For example, try to understand the brain neuron functionality, intelligent approaches. So we discussed that in the paper. And then in the 5G systems, the revolution from the 4G to 5G, a lot of people, they think that everything is almost the same, but the revolutionary step was that we started to do software-defined networking and network function virtualization. It's kind of like the softwareization. That was the big step. For example, from 3G to 4G, the big step was the MIMOs, like the multiple antennas, as well as the OFDM technology, right? That was the revolution. But here in the 4G to 5G, it's SDN and network function virtualization, meaning resource slicing. And for that, a lot of research has been done the last 10 years again for the 5G, but we will continue to use that approach, but then we will do more automatic slicing. So that's really a challenging problem. There are some solutions existing, so that will continue. And then also this energy harvesting is a big problem in 5G, and it will continue. And there are some ideas about so-called ambient backscatter communications. When you transmit, you also leak energy, and then the approach is how can we harvest that energy back to the transmitter so that we can keep the energy level high, and that's called ambient backscatter communications. And again, a lot of research is being conducted there. And also massive MIMO, of course, it will continue. So we have a suggestion, you will see that ultra massive MIMO, a very large number of antennas. And then cell-free goes with the softwareization. No more these base stations and cell structures, but it will be like all available geographically. And then, you know, this base station concept goes to so-called virtual base stations. And then, you know, the many cells could be like dynamically, virtually formed. And that's the point here. And then we have like these three I put underneath. It's more like the 7G after 2025, 2030, like quantum communications. Again, that's a very hot topic. Everybody talks about it, like especially quantum computing. My personal opinion is the progress is very slow. The quantum computing is here since 2015, 20 years, and the progress is slow. Similarly, quantum communications is now active, and you know, the outcome is really not there what we expect. For example, you cannot have these big data centers in the mobile systems, right? How will you carry that in your pocket? So it would be a need for a new, as an example, mobile device which can do quantum communications, right, and quantum computing. And anyhow, so people are writing papers, right? And then, as Bujar said, I do this research since 15 years, nanoscale machines and also bio-nanoscale machines for the human health. And there is a lot of progress going on here, like molecular communication, health applications, virus detections, bacteria detection. So I wish I could give you one talk about this alone, right? And so unfortunately, I will just cover these green areas and then a little bit yellow because I will show you how I ended up in terahertz band communication. So, you know, here is the thing that I tell to the young people. So it's not like I always give the background stories about my research. It's not like I get up in the morning and I say, oh, everybody does nano stuff, let me do this, or everybody does terahertz, oh, let me do this. That's not the right approach, in my opinion, and my suggestion. So that's why I always give this background story. So you will hear that also. So as you see here, how did I end up in terahertz band, right? So, 2005, 4 of my PhD students were on the market for academic positions, and they kept coming back and saying, you know, everybody's looking for nanotechnology people. And so I got interested in nanotechnology. You know, I remember my times in 1975, the microtechnology, like 74, when the microchips start to come out. So then I realized that what will happen, you know, majority of the research was done on the material level as well as on the device level. And, you know, coming from the communications perspective, I wanted to know when these devices are existing, how will they communicate, right? It happened the same thing with the micro devices. So that's why I started that work in 2006, 7. And so those 4 guys found jobs, and they are now very famous senior people. I'm sure you know their names, but anyhow, they're all in academia. Now, some of them are chair professors. But anyhow, so I wrote this paper. The first one was 2008 about nanoscale machines. And then we published this in 2010, Internet of Nano Things. And that time, a lot of people, when I gave keynotes, they were saying, oh, what the hell is this? You know, it's too futuristic, etc. And, but, you know, for the young people, when you do something brand new, you will have a lot of bastards, they will attack you. Just ignore them, right? So here's the proof. Like Scientific America, they published an article, Top 10 Emerging Technologies of 2016, Internet of Things goes nano, and this link is still active, by the way. And then Market, 2020, there was this IoT market report. As you see, all these companies are into this market of Internet of Nano Things. So, you know, people, they were attacking or saying this is science fiction. Now it's coming, right? So, so that's why we started to work on this nanoscale machines. And then we realized that all these components, which we designed by this way, this nanoscale machine, like 1 to 10 micrometers, as you see here. And then all these components like nano processor, nano memory, energy harvesting units like nano batteries, and nano sensing and nano actuators, they were all existing separately, but the transceiver and the antenna sides were not there in 2008, 2009. So we said for the communication, we need this, right? This is the front end. So we start to work on this research, like first of all, trying to develop some front end transceivers and antennas, and then all the other components we can put together and then create a nanoscale machine. So that's where we started this work. And, you know, you see here over the years, we had all these funding agencies in the United States. And also I started a research group in Catalonia, in Barcelona. And then I got finished distinguished professor project from the Finnish Academy of Science under FIDI-Pro, then Humboldt Award, and in Saudi Arabia. So, you know, almost 60 people worked over these 15 years on these topics, right? So what we try to do is the big picture over these 15 years work is first we developed or designed transceivers and antennas as front end. And then we observed, we realized based on the material I will explain to you that the materials we used for design of these front ends, we needed to operate them in terahertz band. Now you see how I ended up in terahertz band, right? So then we realized that all these textbooks, papers, they have a lot of work on the channel modeling on the lower frequencies, like, you know, kilohertz, gigahertz, megahertz, but there was nothing that time in terahertz band. So we did a lot of research on that. And you will see some of these ideas that we developed here. And then also on the networking level, all these protocols were missing. So we did some research on that. So I will just try to explain a little bit all these concepts, and then I will continue the lecture with other topics that I present you in the beginning, for example, those reconfigurable intelligent surfaces, for example, and how I ended up there. So when we were trying to design these devices, we ended up in these graphene material. Graphene is two-dimensional. You know, everything is, as you know, it's three-dimensional, but it's so thin, it's like one atom thick. That's why it's like, they call it two-dimensional. The inventors, Gaim and Novoselov, they are professors at the University of Manchester in the United Kingdom, originally from St. Petersburg, not Florida, in Russia. And they received a Nobel Prize in 2010. In fact, I gave a keynote in PMRC September, and I mentioned their names, and I said they will get a Nobel Prize someday. I was hoping, I mean, thinking 2017 or later on, and then 2 weeks later, they announced that these guys got the Nobel Prize. And I have a research center in Moscow, and I know Russia well, and Putin invited them to give them medal, but they did not accept, they didn't go back. Anyhow, so, and also these guys presented the first 1 nanometer transistor in the world, 2008, the smallest one in the world. And also they are participant of a graphene flagship conference, flagship work project in the European community, €1 billion investment by the European community. And Andrea Ferrari is leading from University of Cambridge, but you know, that's the graphene consortium. So what are the other interesting things? It's world thinnest and lightest material, world's strongest material, harder than diamond, 300 times stronger than steel. They take any forms because they're bendable, and they conduct electricity much better than the fiber and copper. transparent material, and also very good sensing capabilities. These are the nano material, right? Graphene, and it's a big jump. And so that's, not only you can use this in the IT technology, like all these processors, memories, batteries, antennas, etc., but also you can use them for, plane productions, automobile productions, laptops, anything you can imagine, right? Like, some of you old enough, they may know that aluminum was not here in the 60s, or plastic, for example. The same thing with these graphene. The only problem is it's still expensive, the good quality graphene. So we use this graphene to develop these antenna. And so as you see here, we published some papers, and also we got the patent. It took very long time. It took very long time because CIA put a lock on it for a couple of years, and then they released it, and then finally we got it 17. So the basic idea is, as you see here, there is gallium nitride or gallium arsenide dielectric material, the gray area, and you put this patch, this graphene, on top of this dielectric material, and then you hit the electromagnetic waves, and then there are these global oscillations of the electrical charge between this graphene on the surface underneath the dielectric material, and they glide through it. And it's called radiation of surface plasma polarity waves. And we realized that this SPP, surface plasma polarity waves, work the best based on the graphene material and the higher frequencies, like 100 gigahertz up to 10 terahertz band. So when we went down 60 gigahertz or lower, like 2, 3, 4, 5 gigahertz, then the performance was not the best. That's why we ended up in the terahertz band, right? So the many details you can find in these publications. And similarly, we developed this transceiver. As you see here again, this dielectric material on top these graphene, and then the transceiver based on this HEMT technology called high electron mobility transistor. And we also got a patent, as you see here, 2016. And although we applied for patent later on, and it got faster, So again, there are many details I will just skip here. And then you see, as a result, it looks huge, right? But it's very small, right? So we have this, we call this front end, the transmitter, like the transceiver, let's say, as the plasmonic source and the modulator and the antenna. And then, we can transmit. So and the receiver side, of course, there were many other research, like synchronization issues, equalization. When you check those boxes, you will see all these problems that appeared in the high frequency bands, and also because of these new devices, we try to solve them, right? So now that's why, so that's the background story. Again, since we're not talking about nanoscale machines, so we ended up in terahertz band. By the way, I have to explain to you that, in order to operate the terahertz bands, we do not need all these nanoscale machines, right? You can also use these classical materials, and there are some devices existing like 300 gigahertz, even some, 500 gigahertz, classical materials without nanomaterials, and then they work on terahertz band, but very, very limited distance, right? In a lab space. I will discuss that to you. So in other words, I gave you this example with the nanoscale and graphenes because I ended up here, but you don't need to come from that direction, right? There are a lot of people in the meantime. That time they said it's all, terahertz band is too far and it's not realistic. Now, when you look around, please check with Google. Tons of papers are getting written on terahertz band. And then accordingly, we got citations, right? Here are the two papers that we put together with my former students that are professors also in Northeastern, Josep Jornet from Barcelona, and then Chang Han is University of Michigan in Shanghai. And so they continue also their own research, right? So, so what did we do here? That's what I want to show you. So we first start to understand how the terahertz band works, right? So we published this in the journal here, transactionwires.com. And again, I will skip the mathematics, and I want to show you what we learn out of this. So first of all, we put these devices, say, in certain distances, like 1 meter to about 1 kilometer. And in the beginning, we use COMSOL simulation. It's a physics simulation tool. And so that's why we could go up to 1 kilometer, right? And then we run and, you know, based on our mathematical model, try to find out what is the path loss, you know? So as you see here, the red area is like the path loss is so high, you cannot have meaningful communication. So in the terahertz band. And then when you go lower, then you have these sub windows, sub bands, as you see here. Of course, when you blow them up, so you can go higher distances, right? These lighter areas. And then in short distances, it's a crystal clear channel. You can have meaningful communication, right? So so first of all, we did a lot of COMSOL simulations, but also we validated our results. We had some test bed here on 300 gigahertz. Like you can see here, these frequency bands from like 100 gigahertz up to 10 terahertz. These areas are all with the COMSOL simulations, and then 500 gigahertz and lower. We validate these results with the measurements, okay? So why is the problem, right? So first of all, when you work with the millimeter wave bands, the enemy in the 60 gigahertz around is the oxygen particles, right? Oxygen. But when you go to higher bands, the biggest enemy is the water particles, because there are a lot of water particles that affect the signal propagation, and accordingly, the path loss gets higher. So in other words, especially when you go higher distances, those water particles affect the signal propagation more. That's why we are distance limited, you know. But what is the advantage of terahertz? You have terabytes of, you know, all these objectives that we are talking about for 60 gigahertz. You can reach that in these frequency bands, but they are distance limited. So I detect this, you know, we detect this back in 2010, 11. And since then, we have been working on how do we combat this problem. And as you see here, all this work we did in the meantime, we published in 2018 with my another PhD student who finished now, and Shuaini. So what we did is we tried to find out how can we increase the distance, right? Because if you cannot combat this distance problem, nobody will use it, right? So like this was in the 90s, ultra wideband systems, they never made it because they had this distance problem. So now what we tried is, as I told you, we looked at, again, when you have some physical layer channel modeling idea, there are so-called multipath effects. There are positive and negative effects. When there are positive effects, then you can somehow increase the distance, because when these signals are spreading out and then, you know, they all hit the same destination, then, you know, that's a positive effect, that the signal strength will be higher, right? So we show that in this paper here. And then another thing, what we try to do is we use this these subbands, as you see here, these windows, sub windows, and then because the distances could be higher, right? And then we try to do so-called distance adaptive modulation so that we can utilize them. But the only problem was we were using these subbands. The bandwidth that we were having was not that this entire terahertz band, right? So we published that also here. And then we observed that we could really increase the distance, but not enough, right? So that, you know, that for the practical purposes. And then we came up with this ultra massive MIMO idea, because this massive MIMO is there since, you know, again, 10 years. So we've tried to find out if we increase the number of antennas, because then we will create these beamforms. I will show it to you. Then we can go to longer distances, right? And I will explain that to you. And then the next one was, you know, that now you see that how I ended up with this intelligent environment, or so-called reconfigurable intelligent surfaces, again, to help for the distance combating. You see how you know, all these years, you know, so how we came up with these problems. So I explained to you that, you know, these multipath effects, that we can increase the distances. And also with this distance adaptive modulation, how we do it. I explained to you that we are using these windows, and then we try to modulate adaptively using those sub-windows. And then this ultramassive MIMO idea was based on our plasmonic nano antenna that I explained to you, the patent we received. And now you see here, although we did this much later, we got the same year the patent on this also ultramassive MIMO. The good news is now a lot of people are working on these ultramassive MIMO, so it's good news, right? For other purposes, right? So as you see here, we are using these planar array with 32 by 32 antenna elements in total of 1024 elements. It's a gigantic step, right? And then, as you know, that in the MIMOs, you have to have certain distances between these antennas to avoid these interferences. Because we are using plasmonic nano antennas, you can have, you know, shorter distances. These are the wavelengths, right? Surface plasma polarity waves, and then you can put them into the surface. It's a very small surface, and then you create this, gigantic ultramassive MIMO platform. And then we did a lot of investigation. We could get tenfold increase in the transmission distance with these ultramassive MIMO, and then we use this more. That to show that, it's a very powerful idea. It's called dynamic ultramassive MIMO. So for example, we can use these antenna elements, arrays. We can create different heterogeneous multi-beam forms, right? So now, by properly feeding antenna elements, antenna array can be dynamically switched among different modes. Like as you see here, certain parts can use this beam form, this one, etc. It's again dynamic. We call this ultra massive spatial multiplexing, but also we can let them work all together, create these single focus beam like razor sharp, and then you can go much longer distances. By the way, US Army, I was in a strategic planning meeting in October, November. They are called this directional networking. Not directional antenna is there, right? But they are calling directional networking now with all these single focus beams and adaptive beam forms and etc. Right? And then we also have these multi-band, kind of like heterogeneous ultramassive MIMO. As you see here, we can have different frequency bands, and then again the antennas can be locked in these different bands, and then do transmission and reception. This also goes with our reconfigurable front ends, as I mentioned, one of the topics in 6G, right? So now there are many challenges, of course. Ultramassive MIMO, not only us, but also other people are conducting that research, because we have like thousands of these, what is it called? These antenna elements. Then how do you estimate channel coefficients and antenna spatial correlations, and then also especially estimation of these channel conditions, right? And then how do we come up with these dynamic modes, like dynamic and multi-band modes, and realizing them, right? And then, of course, codebook design, antenna area element optimal control, and different beam formings. Like for codebook design, we have this paper which appeared in ICASP, and it will appear in transaction communications with this girl. So now, so this is a little bit about ultramassive MIMO now. So now this is intelligent environments that I will show you. So like, as again, reconfigure intelligent surfaces. So far, I explained this to you. So now, before I start these reconfigure intelligent surfaces, I want to share you my experience in 40 years. So when you talk to the people in the 80s, again, I'm sure many of you are too young to remember that, maybe younger than 40. When you ask people, what do you do? They said, we do high-speed networking, research, information superhighway. And then late 80s, everybody was doing ATM networks. And then early 90s, everybody was doing 2G systems, and then 3G systems. And then, like later on, of course, 4G systems, MIMOs and OFDM. And now this is the problem now, right? Reconfigure intelligent services. Somebody gets up and says, oh, everybody is working on this. Let me write another paper for that. So you see how I ended up there is that I try to increase the distance in terahertz band communication. In 2011, I gave a keynote speech. You see, I tell you the background stories, right? In Cyprus, and there was a guy, even he attacked me about, really, it's sad, but anyhow, but what can you do? So, and then that time there were these, it was Cyprus, my colleagues and friends, like my brothers, we know each other since many years. So they said, we should maybe look into these surfaces. And then we start to work on this idea, 2012. And then we started to apply for Future Emerging Technology European Community FET project. Very, very challenging, 3% acceptance rate. We were rejected 3 times. You see, it's a good example for you. Never give up. So believe in yourself. And then finally we got it, So I will explain to you what we did. And now the last 2 years, a lot of people woke up and said, oh, let's start reconfigurable intelligent surfaces. What can you do? But it's good that we are getting citations about our papers. So we have these 2 designs. One is in Georgia Tech that I use some of our ultra-massive MIMO platform that I told you. And then the other design is about Future Emerging Technology Project EU with all these Greek names, as you see here. My name sounds also Greek, but it's Turkish, means white star, in case some of you don't know. But anyhow, so we started back in 12, 13. We published the first one in 15, and then we got a patent also. So it's good that we did all this work. By the way, I'll show you more about it. So now, in the meantime, in the beginning, we called this like hypersurfaces, metasurfaces, in intelligent environments. Now, there are many names are floating around, like reconfiguring intelligent surfaces. All of these you can read here, right? So everybody's using something, and but it's plus minus the same. So why do we need intelligent communication environments, right? So thanks God, in the wireless communication, electromagnetic waves undergo multiple uncontrollable alterations as they propagate through a wireless environment, right? All these issues like shadowing, reflection, refraction, scatterings, absorptions, like, resulting in path losses and attenuations, for example, right? Thanks God this is happening, and interferences, non-line of sight problem, fading, Doppler effects, and then the coverage areas, right? Energy consumption, security. So that's why I said, thanks God, these are existing so that we make money out of it, right? We find jobs, we get masters and PhDs, and we work on these topics. And, since many years, many decades, right? We try to solve these problems. Unfortunately, we cannot solve it totally, right? Like there are physical layer solutions like adaptive antennas, massive MIMOs, multi-user MIMOs, all types of MIMOs, beamformings, adaptive modulation, name them on the physical layer, tons of MAC and routing protocols, hundreds of thousands of papers have been written. They're all successful in a certain level, but they have all separate degrees of efficiency, right? So, it's kind of like a vitamin, solving something, but it doesn't cure you totally, right? So now, so in order to solve some of these problems, there are also these so-called passive reflect arrays. And, when I announced it some time ago, again, that's called in German Besserwisser, meaning he knows everything best. He says, oh, these are old reflect arrays. That can happen to you too. When you have something brand new, somebody will shoot you and say, oh, I know this since 20, 30 years. Just ignore it, please, especially young people, right? Just move on, because there are all these bastards out there, they will attack you. So anyhow, so reflect arrays. So these are like these passive arrays, like, when the waves or signals hit, they're just reflected, right? Like passively, right? And then there were these relay concepts, right? And there are relays, and then they have these MAC and routing layers in the software protocol stack. And then, they process and then they hop to the next one. There's also a lot of research has been done on relays also the last several years. But now the problem is when you inject these relays, then you inject latency because you have these processing in these relays, and you will screw up the end-to-end latency in the 6G or even in 5G environments, right? So now, you cannot use these here. And so this concept started with these reconfigurable intelligent surfaces. The overall objective is how can we turn intelligent, this passive, inactive wireless propagation environments or wireless channels into intelligent communication environments as active participants in wireless signal transmission. Not like passively reflecting or processing, but then everybody will, when you start a new company, immediately the investors will ask you, what is the secret sauce, right? There is a secret sauce. So the secret sauce is the following, that the material that you are using here, like metamaterial, for example, or graphene, and they have these intrinsic characteristics, they will help us to do all these manipulations of the signals coming in automatically, okay? So some more interesting thing is these are the passive patches, and then there is this switch, like these one. They're either pin diodes or varactors or MEM switches or nanocontrollers, again, based on the designs of people in the world. They're working on these. And so these are these so-called switches. And then there's these controllers that can be wirelessly or wiredly connected to these surfaces. And then like microcontrollers, or some designs are based on FPGAs. And there are some coding sequences like codebook in the CDMA, for example, like codebook design that they will represent different states of the switches, right? Ones and zeros mostly. So what happens is, as I explained to you, because of the makeup of these surfaces, they can support when the signals, waves hit, they can be control reflected, or they can be phase shifted. They can do polarized reflections. They can do collimate, specular reflection, splitting, focusing, as you see here, or absorption. So that's really a fantastic idea, right? So and so there are many applications you can imagine. Like for us, it was more for terahertz band distance extension, but you can do, also try to attack those wireless channel problems, right? The ones that I showed you, kind of like mitigating the wireless channel effects and have better communication, right? So now in the meantime, as I told you, there are thousands of papers. Somebody gets up, oh, I can use it in the bathroom. Oh, I can use it in the satellite. Oh, I can use it in the cars. Oh, I can use it in my bedroom. It's unbelievable, So, and majority of the people, like most of the telecom people, they don't care about this box, right? They just say, oh, the signals come in, they somehow leave, and I'm just doing mathematical modeling. That's not the right approach, right? So it doesn't help us to progress, right? So now what else can we do with these, right? Intrinsically, I told you that you can do a lot of control of these signal propagations. For example, if I have a user A here, which needs to objective is optimizing its quality of service, or if you have users which are unauthorized, we want to block them, and that's the source. For example, transmit to the user A or to the user whatever here B, for example, and each of them may have different objectives, right? Like again, security, we can avoid eavesdroppers or these unauthorized users through these these intelligent surfaces, in other words. That's what we showed also in this paper. There are many benefits, like we can optimize beamforming and spatial diversity, and resource allocation we can do much more intelligent way, like spatial, spectral, and temporal considerations. And also it goes with those automatic slicing, right? Virtual network function visualization. You can do that also with these surfaces. And then you can do a better tracking of the mobile users. We can maximize data rates, optimum adaptive decisions, and wireless power transfer, and of course, security reasons. And also, very recently, we have a paper, unfortunately it's not published, but it's under consideration. We also use this for ambient backscatter communication, by the way, how we can do energy harvesting through these surfaces. So if you're interested, when the paper's out, I can send it to you. So it's really another step, really, because everybody does, you know, more and more surfaces. We are trying to branch out. What else can we do with those, right? So now, again, the entire world is working on this. This is for your own interest that you can go. And if your department is doing research, it's not there, I apologize. So, you know, all around the world, even my Russian, Moscow, Russian Academy of Sciences, I have this wall project, or had, we have finished it with Huawei, and then hypersurfaces, and then this, and of course, all the other countries and universities and companies are doing this research, right? All they do here is, and everybody has a different objective, right? So like, for example, our hypersurface research European community that we are writing all these papers, we are looking at 2.5 and 60 gigahertz, even higher, you know, sub-terahertz, like 300, 500 gigahertz. And the other ones like lower frequency bands, as you see here. And then they are different, using different materials, and then different sizes, you know. So there's nothing standardized, by the way. Everybody has its own functionality objectives, and then also like configuration of the control, like microcontrollers or FPGA designs. So same thing here. It just gives you the overall picture. Maybe there are hundreds more in the meantime, because everybody does this research now, as I told you, right? So I will go immediately to the, because it's 11:50 now, I have 15 minutes. So I will explain you some of these ideas that we did. Let me go to this. Yeah, we had all these mathematical models, etc. So for example, here is a case with the surfaces. We had one transmitter and let's say 12 or 15 receivers, non-line of sight. We operate them in terahertz band. The path loss is so bad we couldn't do it. But as soon as we put intelligent, you know, walls, environments, then we could get very good performance, as you see here, with these intelligent surfaces. So I want to tell you more about this Wiser Surf research. And so it was, we finished it after 42 months. End of January, we had this final review. The coordinator was the 4th research center in Crete, and we got like almost 8 million euro together. And then the partners were University of Cyprus, Fraunhofer Institute in Berlin, Signal Generics, small company in Cyprus, Barcelona, Catalonia, and Aalto University. And we were like almost 30 to 40 people in all aspects, you know, from the like computer science, electrical engineering, telecom, antenna, hardware design, chip design, material design, name them. They were all there. So you can see this was the one of the meetings in August 2019 in Cyprus and Crete. So we can see this is the European community guy who came for the review. So many people were in the toilet and all that stuff during the break. And they were fantastic young people. You can see, really, I personally enjoy the work with them. I'm here. I really miss those days. Anyhow, so you know, we worked together, all this, you know, from material and all this. And so what is the secret sauce? Remember, I explained to you. So a metamaterial means in Greek beyond, is a material engineered to have property that is not found in the nature. So when we try to manipulate electromagnetic waves, like for example, block, absorb, enhance, or bend waves to achieve benefits that go beyond what is possible with conventional materials, okay? And their precise shape, as you can see here, geometry, size, orientation, and arrangements gives them the smart properties or intrinsic properties to do all these functionalities, you know, manipulating these signals, right, or the waves. So this is a prototype design, physical hardware platform that we developed here. So now you can see, like here, one of this here, like schematics of elementary cell. So what it does is completely re-engineer coming electromagnetic waves automatically, right? So like you can do, you know, it does all the steer, absorbing, polarizing, all of these automatically. So that's the advantage of it. So now we use this. As you see, the platform I showed you here is on this green, like this patch and also these controllers here, right? And then, you know, when you blow up one of these, that's the one that we got patent. So you can see there are matter atoms and metallic patches, and then we call them unicell, and there are these sensing units. We also have a further design without sensors, you know. Anyhow, so that's we call this metasurface layer. And then we have this switch configuration. That means that these switches that we showed you, like in these here, they allow programmer to customize, deploy, or retract functionalities on demand via access point interfaces. And then we have these EM function layer. These are all virtual layers, right? And they do all this functionalities, absorbing and steering, etc. And then we have this gateway or the microcontroller, we call them, right? Either wireless, you know, we have this wireless, or you can also do wire, right? And then this one controller can control multiple of these. I will point them out to you. So now you see some of these. Again, we publish, I don't know, 100 papers. When you go to wisersurf.eu, you can see all the papers, you know, all these different aspects, right? Not everything on telecom. So, for example, we showed in this paper that we can do these maximizing the receive power and also optimizing the power delay profiles for the users here, just a study, for example. And then we published this paper that works with the SDN and FV, like SDN controllers in 5G, that these surfaces can be controlled by these controllers in this, you know, SDN and NFV architecture, right? And then also we have this, you know, how can you sense the incoming wave directions, right? Because this is the, you know, the surface, you know, the antennas, I mean, the signals are hitting them, right? And how will they know what to do with these incoming waves, right? So it's called like impinging waves, right? So what we try to do is we determine the attributes, for example, the direction and polarization of an impinging wave by matching with the surface impedance, right? These are the surface impedances. And when the wave is fully absorbed by these surfaces. And then accordingly, we can control them. There are, again, many details that, you know, you can find in our website. So we did prototyping, as you see here. This was like 1,200 euro to produce 1 by 1 meter, for example. And then we, you know, a lot of, again, results are there, you know, performances, etc. There are many open research issues here. Like, for example, still resource allocation. And again, we did our research, but that doesn't mean it's done. So there is still more. Fair scheduling algorithms are needed. Then we need optimization, like, you know, for example, if you have a very large number of devices like IoTs or massive IoTs in the 5G, how do we deploy these platforms? High demands of real-time video streaming, higher mobility, etc. Then also, like I mentioned this to you last year, and there are some papers already, if some of these units malfunction, for example, how do we tolerate fault tolerance and also like the reliability issues, right? How will the individual unit failures affect the beam patterns? That's the question. And then another question here is, again, multiple surfaces deployments, because we will have multi-hopping, right? And then they need to be coordinated. And also the optimum size of these platforms, right? And optimal locations, and a topology control problem. And that's not that easy, by the way. And then, of course, when you have multiple of these multi-hopping routing algorithms needed, if you have multiple users, how do you take care of these multi-access, right? Like MAC protocol types. And then, again, really, I want to encourage people, they do this research, please stop writing more and more papers. Try to show us at least one case, like Wi-Fi environment, that it works, or a little IoT, it works. Enough theory writing papers, mathematical, yet another one. So just show like this gap, right? So how it works, right? And then, we already started, but some also people did, AI and machine learning to make these surfaces more intelligent. So another issue here is, as I explained to you, how will you incorporate these surfaces into 5G, 6G, 8.11 IoT architecture, right? So that's the gap. And then standardization committee is missing. Like, like what is the transmit power? The frequency bands, I told you, we worked on the lower frequency bands and also in the terahertz bands. That's what was our beginning for the terahertz band, right? So then when we go to terahertz band communication outdoor scenarios, right? Majority of the people in terahertz band is working indoors, right? So when you go to outdoors, we can also use these platforms, right? And then, we will have longer transmission distances. That means higher attenuation, stronger shallowing effects, higher single energy dispersion, and then of course higher mobility, and then according scattering environments and more larger Doppler shifts, right? And then how will we use these surfaces for outdoors, for terahertz band, mobile communications, multi-hopping, right? And then how do we use multi-band ultramassive MIMO in terahertz band multi-hopping with adaptive modulation techniques, for example, and coding. So now the terahertz band, going back there is an interest group, 100 gigabit per second. They meet every 2 months. And Tom Kerner from Braunschweig is leading that. And then we have this interest group that looks, since many years, 300 gigahertz to 3 terahertz. So now there is also a workshop that we organized since 3-4 years with Globecom and ICC. This year we have another one, ICC. And also we have a special issue in the IEEE JSAC on terahertz band communication, which will appear in April. So now, what are the lessons that DARPA is the unit that started the internet, right? So they published this article, 4 DARPA projects bigger than the internet in 2014, as you see here: atomic GPS, then virus shield for Internet of Things, and rapid threat assessment. Last but not least, you see, people were attacking me that time: terahertz frequency electronics devices, metamaterials, and communication. So now we are on the target, right? So like 7 years ago. Now, so why is this here now? We forgot that. I didn't delete these parts because I tried to match them. So last part, I have like 6 minutes. I want to talk about CubeSats, right? So I covered these, right? I hope you are following me. And so now the issue here is there is IoT on the Earth's surface, right? How can we create also IoT in the space, right? So that's the objective. And so now we have all these LEO satellites, MEO geos, and drones, and that's a hot topic now. So can we also create CubeSats, right? So the base background story is quickly. So I was invited by University of New Mexico. Again, I explained here the background story. It's not like I got up and said, "Oh, CubeSats, let's start." So I did a lot of research. When you check my background in the late 90s, early 2000s for NASA, and a lot, for satellites as well as for interplanetary internet. And then I got out. The NASA had some money problems, so I did not do research since 2005. So 2017 or 16, I don't remember now. So I was invited to University of New Mexico, and I gave a talk about these, 5G, 6G type. And then there is this Air Force Research Lab there. And then they showed me about CubeSats. I heard about it, but I said, forget it. And then when I saw that there, I said, my God, there is a future for this. So when I came back, I said, let's start research on this, right? So now we wrote papers here, and it takes some time, right, to come up with these things. Now and then we applied 3 patents in the meantime. So now here's another lesson for the young people. So when you start something new, You cannot say, oh, let me start and then write another paper. You will not make the impact. So now when I solved that thing, so I was trying to find a corner angle to come in with a big impact, right? I mean, you cannot say, oh, I'm doing another CubeSat and then so what? You know, so I tried to find that angle. That's why I will present to you now, right? So that's the thing. You cannot say, oh, let me write another paper. So that's the thing about LEO and all these other satellites need very long time for development and deployment, like sometimes 7 years, a lot of money, construction and launching costs. For example, a failure Hitomi telescope in 2016, it costed them $300 million in 10 years of research. So now this CubeSats is really interesting topic, and it was done, many years ago. Normally, when the inventions come from the top 10 schools in the companies, so the Cal Poly is a teaching university, California State University. There was a guy who came up with this CubeSat, as you see here. So that's a cube style. It's very, very easy to, if you know a little bit of electronics, you can build your own CubeSat, really. So they called it that time nano micro satellites. And then the unit is 1U, 10 by 10 by 10 centimeters, or 3U, 30 by 30 by 30, or 5U, 50 by, etc. Right? So that's the unit. And it's very simple, like to launch them. It's like, you can produce them, hundreds of them, you launch them easily, and then when they die, so what? It's not that expensive technology, right? They are scalable, flexible, etc. There are many, many advantages, right? So now, again, due to time, I'm trying to be a little bit faster. So they have these electrical power system, command and data handling, attitude like navigation, determination and control, payloads, and communication systems. And there are existing systems, by the way, here, like, Elon Musk, he has this Tintin SpaceX company, Tintin. Here is a one, right? He's his own, like 7,000 satellites, etc. Like Iridium Next, Astrocast, Switzerland, Australia. So they're already existing. Remember, I told you that, and also other universities have their own, at Georgia Tech Aerospace Engineering, they have their design. So what did, I wanted to find a, niche to come in. So most of them are using single or, the double frequency bands, frequency spectrum bands, or Ka, like Tintin uses V or Ka, Ku bands, and L bands. So it's all like compartmentalized again. So I wanted to have the following case. So quickly. So first of all, I said in this space, there are no water particles. I can operate them in terahertz band. And then there's no distance problem, right? So that would be terahertz band. Going up and down, there are these atmospheric effects. I cannot operate them in terahertz band because there is distance problem, right? And, there are some people, oh, we'll put some surface, joke, right? So anyhow, so then we said, okay, can I use reconfigurable front ends like here? That means they will operate in these bands, like dynamically, C bands, X band, Ka band, military bands, and terahertz frequency bands, but seamlessly, right? So that's the thing, that we developed these front ends that I was telling you about, reconfigurable front end with the transceiver antennas, that they will operate seamlessly in this, going up and down. And then, of course, they must have also dynamic, these front ends, so they can operate them in the terahertz, right? So that's what we did, a lot of research on this the last 4 or 5 years. And again, our design is shown here. Again, I have to finish this. And then another novelty was that, based on my past experience, I did not want to put software on these devices. Everything would be like software-defined control from the surface, right? And then controllers are on the Earth surface, and there will be signaling to these devices what to do. Is exactly going with the 5G and 6G architecture, right? Softwareization, software-defined, and network function virtualization. That's what we did. And then again, we published a lot of papers, and these two students wrote, like this, Ahan graduated last month. So there are many open research issues also here. I was a little bit fast in the second part, but I hope you got the point. I thank you. It's exactly 12:07. I think I started exactly 1 hour ago. And I hope I did not burn your brains with all these, you know, many research directions. And if you have questions, I'll be glad to answer them. Thank you.
Thank you so much, Professor Jan. And now it's time for questions. You can write, or if there are no questions written until now, maybe you can do directly.
Can I ask something?
Yes.
I'm interested because I'm working mainly now with underwater sensors. And do you think it can be easy to have this cubes set that you say, to have also some connection, good connection also with a applying sensor that can be in underwater? Or you think that is quite impossible?
Actually, very good question. And I have a research group in Abu Dhabi, really. So I'm opening this underwater chapter. Sorry, I'm getting alarm system here, and I had one, but we are putting video. That's why you are hearing the signals. They are supposed to come yesterday, but anyhow. So this, where is this underwater case? No, wait a second. I show you what I wanted. Hallelujah. Okay, here we go. I have to close this one. I told him not to. I close this thing, right? What the hell is he doing now? So I have to open this new one.
Probably you have to stop sharing.
I did just, yeah, exactly. I have something more to say. So anyhow, so here we go for the underwater things. I have another keynote on that one. Where is the, there are many things here. 1 second. Okay, so the question you asked me about is dynamic, right? Underwater, is that the question? Can you repeat that, Alma?
Yes, that was
okay. So here I have this idea about I call this I deleted that. Why did I delete that? Oh, here we go. Yeah, cube UWatt, exactly. Bravo. Exactly. You see, I was going to, here's a background story, to give a keynote underwater in Shenzhen. And in LA, I remembered, why don't I have something on cube UWatts, underwater CubeSats, right? I mean, cube UWatts, I call this. So I explained this to them, right? So now here's the thing that we have. So like you will put like these, the channel and data handling here, and communication subsystem payloads and all these energy power systems. And you can have these like this static cube UWatts or mobile cube UWatts like this. And then like you can have them underwater like anchored here. And then also like these mobile ones, they can move around, right? And then, you know, that's what we can also put the SDN on these buoys here. That's, I suggested that, right? Hardware design, software development, and then all the challenges here. So you read my mind, and so we have that already. I mean, ideas, right? So there are no existing solutions. For the time being, what I'm trying to hear, design of cube UWatts, it's called, right? And then for the time being, we are working on this surfaces for underwater, because everybody works on the terrestrial. And one of the biggest problems of the underwater is the data rates. You know, we are using acoustic communication. We are stuck with kilobit per second rates. So now that's a grand challenge, how we can increase the data rates. So people are trying to do with these massive MIMOs, right? You know, beamformings to, again, increase the distance. Same problem as I told you in terrestrial and terrestrial, right? And now here, so we tried to do this ultramassive MIMO, again, for acoustic, try to increase. And another idea that we are currently working on, and we have some ideas we'll publish soon, is can we use these surfaces, but it's an acoustic base, you know, underwater, and then solve the problem. And then we had some design ideas here, right? So, so good question.
Okay, we have another question from Professor Enver Hamiti. Professor, would you like to ask for a question, or I?
Okay, it is written. Professor Jan, thank you again very much for your very inspiring ideas, even if it was too speed, comparing to many knowledges, new ideas, new developments, and so on. But again, thank you. And I would like just to ask you if you can say me something more about full assessment of reflection, transmission, scattering, etc., of building materials. Do we have enough studies?
Yes, we have. I mean, I have like tons of slides. Again, you know, I could have just given you one talk about surface and cover everything, but I thought it's better I give you a little bit explanation, and then you can go and read more of the papers that we have, also other papers. So now you're saying like these here, right? Like the
yes, thank you.
Right here. So what do you want to know? So there are many, like, you know, solutions that we worked on. I hope I could find them, you know. So for example, how do you establish, right? So suppose you're a transmitter here, receiver here, right? So now you need a connection setup, right? So how you design those? So we have all these studies done, like handshake, and then how the signals are hitting here, and they're absorbed, for example, like here, or reflected, phase shifting. We develop mathematical models, formulas, and then we show that indeed they can do these functionalities intrinsically controlled by these microcontrollers. So they're all there, and I hope I could find it. Where is that now? I'll go download. So, but if you have specific questions you want to know, I can help you. Let me open this. Oh, here we go. So we are having a new project with Huawei for embedding them in the 5G. I cannot tell you more, but you can see that, like, you know, we can create these configurations. You can see on the surface, right? And then they can do like decisions about what to do with these incoming signals. For that, we have also some functionalities that we call them Xi formulas, like you can see here. How do we set up the connections with these Xi formulas, optimization, and then how they are controlled by, you know, you see this compiler by a computer here, controls them, and then also do multi-hopping. So, and then of course, all of these functionalities, how we realize them. So that's all in the, again, you know, people, the real design people have different approaches, how they control these, you know, these functionalities, right? So we are using metamaterials, and they are programmable, and then we program them, and then we put them here, and then we also put machine learning algorithms. They learn as they, you know, they program, and then they know what to do when these signals hit what type of functionalities they will apply intrinsically. Again, there are no delays, please, because people think that there will be delays or they're just dumb reflections. No, that's what, the differences to the relays as well as to the passive reflect arrays, right? So that's what we do, okay? And there are, again, we had the tutorials in Globecom and PMRC, details, because we were like 3-4 hours like talking about it. But if you go through our papers and then you don't understand something, you're welcome to come back to me. But this is the start for people that they want to get into this topic, right? At least they know, the basic ideas, and then they can go and see what can be done, right?
We have another question from Fiola Demay from Silicon Austria Lab. Is Fiola here, or I can just read the question? Okay, I will just...
Yes, I'm here.
Okay.
So my question would be, first of all, I would like to thank you for the very interesting topics and an overview of a more long-term perspective. My question would be where or in which use cases you see the applicability of terahertz communications in the future. You mentioned that the focus is right now mostly indoors. And I also know a use case, for example, for the train wagon coupling with a very short distance. But do you think it can be possible to be also used in outdoor scenarios, and where, if yes?
Okay, so when you look at the 6G use cases, like virtual reality, for example, right? And then all these very high volume traffic communications. In fact, I wish I had the paper to open here now for you, but there are many applications that they need very high bandwidth, right? So I gave you this augmented virtual reality, for example, all these gamings, and then, high volume, high definition videos and all that stuff. So, and then, holograph, like there are, in other words, whatever you think that there are many high bandwidth demands and high data rates demanding applications that I show you, like we need like terabit per second level, right? And those applications need high frequency bands so that we have this huge bandwidth for the communication. So of course you can use 60 gigahertz, like the millimeter wave bands, but then again, the useful bandwidth in the 60 gigahertz millimeter wave bands is 7 gigahertz. Even that will not be enough long term. That's why, 15 years ago, I said, why should I waste my time only for 7 gigahertz in millimeter wave bands that I jumped to the terahertz band? So that's why, I invested a lot of time, because that's a huge bandwidth. And then we hit the distance problem, right? In fact, that same problem occurs also in the millimeter wave bands, like non-line of sight, etc. So when I was working on terahertz distance problem, and I was also solving the millimeter wave bands problem. So that's why, terahertz band is very, very important for all these up and coming applications, use cases. Even you can use them in the, like later on the satellite communication, automobile industry, right? So they, car-to-car communications or car-to-background communications. And also users, like when you look at 80.11, that, we're talking about like terabit per second now. Like in my home, I just put this new X5, it's called access point. So now really, these are not futuristic anymore. So that's like, indoor, but outdoor also, as I explained to you, there are many, many applications like, cell phones, right? And they will also operate hopefully in very high frequency bands. And then, you can do all these augmented realities and virtual environments and all these applications that we have. And, of course, again, there are problems in outdoor, as I explained to you, like that some of them I pointed them out here. So they need to be solved. And also multi-hopping outdoors. And like maybe also you can put these surfaces if you want. So you know, there are many use cases, in other words. So that's an open issue, or you know, research topic that I highly recommend you. And then you had also a question about sustainability. What do you mean by sustainability? Meaning, can you, you know, there is this word, I know what sustainability, in which context do you mean sustainability? Like,
yes. So I meant it in the context of going more green in terms of not only having the performance as a optimization problem, but also environmental.
So yes, in fact, I apologize because I have another talk about 5G. I do not want to repeat what the 5G objectives are. When you know the 5G's objective is called green communication, that means how can we reduce the energy consumption, right? So that's a big topic and still continuing. And for example, like these base stations, some of them are using diesel, or, you know, these, they also mess up the environment, not just the energy consumption. So, you know, people are trying to find ways of, you know, how can we reduce energy consumption, right? Some of them, they turn off these base stations, etc. So I'm sure you know those. But now it will continue in the 6G. You know, I do not want to put them again, which is continuing. For example, massive MIMOs will continue, right? So I call this ultra massive MIMO, but this will continue. Then another topic is here, the waveforms, right? You know, we ended up with variations of OFDM in the 5G, as you know. Then, you know, well, shall we continue with OFDM, or, you know, variations of OFDM, or shall we come up with a new waveforms? And again, it's a question mark. And then again, based on your sustainability, I mentioned about ambient backscatter communication that goes with your question about energy harvesting, right? So that's, again, a research topic that's really needs to be solved. So it's definitely important, you know, energy harvesting, energy consumption, and, you know, in terms of what you say, sustainability is very, very important. Yes.
Okay, thank you. And we have another question from Vice Dean for Research and International Cooperation, Kadri Suleimani.
Thank you, Professor Bujar. So thank you, Professor Jan, for this great presentation, so extensive and a lot of topics, interesting topics with the latest technologies in 6G and also maybe in 7G. So my question is, you mentioned that there is an open research question, and you mentioned fair scheduling algorithms for multi-users. So my question is, how do you define fairness? So
okay,
what is the objective? Is it resource sharing, or?
So the fairness, you know, again, philosophy here. Unfortunately, there is no fairness in the world, okay? That's very sad. We know that, right? So now the fairness in communications, telecom is defined as, let's say you have multi-users, and each user will get the fair share of the bandwidth, of the power, or resource allocations, whatever he or she needs it, right? Of course, whatever he pays or she pays, and accordingly, the fairness should be satisfied. But on the other hand, if you're a low priority user, and then you pay low, like here's an example, really, just to tell you what fairness means. Like in this case, like I had this lower, like gigabit per second, 300 gigabit per second Wi-Fi access, and then I was paying some amount, and then I'm trying to, because the crime is getting crazy in this country. That's everybody's crazy after America, but there are a lot of problems, as you know, here. My love diminishes about this country, but anyhow, so I'm putting these cameras around the house, and then I needed a terabit per second coverage because of all these video, right? So now I had to get better access point, XFi it's called, and I pay more money, right? So I could not yell at them and say, I'm paying that much money, you have to give me terabit per second. So it doesn't work that way, right? So in other words, fairness is based on what type of user you are. And then accordingly, you will get the fair share, what you need for your communication. So in other words, let's say, you know, multi-user case, right? So like in this case, let me share this here. Multi-users are here, right? Like in this case. And then as an example, multiple transmitters, they try to access, right? And then let's say one person never gets the resource allocation, right? You know, that's very bad design, right? So we have to somehow, that's why we call it fair scheduling, so that, you know, everybody gets what the user demands and needs, like fair treatment, and also their traffic will be fairly, you know, hopped and then receive the destination. So as you know, in the telecommunications, there are many fair scheduling algorithms, you know, hundreds and thousands of them. So it goes that direction, but now it's different because we have these platforms. And then, you know, somehow you must find ways of implementing scheduling algorithms. Again, you know, you cannot implement them here because there's no software here, right? That's everything is controlled by these controllers. And then how will you manage that? And that's why I was talking about it. You know, I hope you get the point about, you know, fairness. And then also you can have a utility function as fairness, you know, mathematical modeling, and then you create these, you know, conditions and then try to optimize it, right? That's the thing I was talking
And the
about.
last question from Ioana Georgi from Manchester University. She has raised a hand.
Oh, so she is in England?
Yeah.
Yeah, I'm in the UK. I'm doing my PhD on cognitive robotics. It's kind of a different topic from what you are engaging with.
So do you know both guys, Gaim and Novoselov?
I'm not sure
You
because
should go and say hi to them, right? So, yeah, go ahead.
yeah, I'm in the School of Computer Science, so I'm not doing telecommunications anymore. More about designing artificial agents. So first of all, thank you for your talk, Professor. My question is, what is your stance on computational challenges of 6G, mainly concerning on-the-fly networks like interconnected self-driving vehicles, or collaborative processing of large amounts of data? So I think these topics, future artificial intelligence, machine learning, and telecommunications will have to collaborate in the future in a much closer manner. So we'll have to think about more deep questions apart from technology and engineering.
Very good question. Bravo. Let me show you. I hope I can find this thing now because I have to stop this and then go there. Very good question. I will start to answer that to you. So now let me stop this thing, stop sharing, right? And then let's go get here. I need this picture. That's why I want to show you about computational challenges and all that stuff, right? So let me, I hope you see this now, right? And let me show you. I'm sorry about the delay here. Here we go, right? But although you see this part, right? I hope you see this. That's nothing underwater, by the way. You can think about this is the terrestrial 5G, 6G systems, right? I mean, I have another picture where it will take me time to get that for you. But the logic is the same. So this is the communication environment, right? Think about from the Internet of Things perspective, right? So now, for all this question about the computational challenges are in this so-called cyber physical system. This is the physical system. This is the cyber system, right? For example, you collect all the data. You get like millions of data, right? So one way is like, how do you reduce the volume of the traffic, right? You can do aggregation, meaning like calibration, similar plus minus information. You can do aggregation fusion. or you can do some statistics like data science, right? Analytics, understanding the value, quality of the information. And then how do you access these huge databases that you will be storing them in your data centers, and you need that information you will get into and then download that information from your data centers. And then you need all this intelligence here, right? And then another thing here is how do you collect data from this physical system environment, right? The field, like you see underwater here, but how, there will be a lot of junk data, and you can have this processing on the field itself also, like maybe aggregation fusion there, and then intelligent devices. They can decide which of the collected information is valuable, which are not. So there are a lot of research needs for the computer science type people that I hope you see what I'm trying to explain you. So there is a lot of room for them to conduct research, right? And like, applying machine learning algorithms to all these devices on the field. And then, again, intelligent collecting of information, quality information, filtering, and transmitting them in the best way possible to the background here. As you see here, these users. Again, the users need a lot of processing too, right? So these are all computational challenges. Moreover, again, damn it, I wish I could prepare all the slides accessible. When you look at, if I have to find this. So again, you have to visualize in your, oh, maybe it's here, right? Let me show you, stop this, and then share this one. No, it's not this one, sorry. Not this one. I stopped this one, right? So let me close this. And then, why is this not working? Not share, let me go back. Share screen. Here we go. So here is another challenge for you, okay? For the computation, because it's a very good question, by the way. So, although again, this shows only the CubeSats part, right? But forget the CubeSats for the time being, focus on underneath, right? So now underneath you see controllers, okay? So these are the exactly going the direction of the 5G and also in the future in the 6G. There are controllers like cloud, for example, but also the controllers, right? They are like data centers or controller hardware. There can be one or multiple of these geographically distributed. And then all the networks on the terrestrial networks, wired or wireless, they will be dumb devices, right? Open flow switches, it's called, or the radio access network will be all software oriented, and everything is controlled by these controllers. So it's like an open architecture. All the software is running here, like the brain, right? And all these organs, I had this picture, but unfortunately, I don't know. So, and the wired, core network and wireless, they are just, brain tells them what to do. That's what they do. So the software is running in these controllers. And that's a lot of computational burdens on these data centers. That can be one or multiple of these. Let's say in Balkan region, you cannot have one, maybe have multiple of these, or in Europe, right, or in England. So then they have to somehow synchronize between each other, and data integrity issues, right, and exchanging the data because they're controlling whatever they're underneath all these switches, open flow switches, or underneath the 5G radio access networks, right? So that's why, as I told you, that there's a lot of, as you can see here, these computational burdens, and like, for example, for the signaling, this brain will signal always back and forth, right? That will cause a lot of signaling overhead. So how do you solve that problem? Again, there are many solutions existing already with patenting and data integrity issues. And now how can you put intelligence into these controllers so that they have faster decisions about set up these connections, etc. So in other words, there are many research open issues. Since you are working on the robotics, and robotics are also part of the Internet of Things, right? Because they are like actuators and they're moving devices, they need to communicate with each other, right? And then you can also do like, software driven, right? So these robots are just bare-bone hardware, and then you have some controllers. They will control them what to do, and they will communicate with each other. They will do actions. So you make the software independent of the hardware. That's the new niche since 8-9 years now. And then have open architecture that you can buy any software from any company. You can put them into controllers. They can control your robots, right? So that's an open architecture idea. Of course, then security is a big problem that you have to, securely protect your controllers, right? So I hope I answered your question. So there are many issues open.
Yeah, thank you, Professor.
Thank you. And before closing the meeting, I ask the Dean of the faculty to say a few words. Professor
Thank you. Thank you, Professor Bujar. I have no question, but on behalf of the Faculty of Electrical and Computer Engineering, I want to thank you very much, Professor Jan, for finding the time to hold this lecture about 6G and beyond, the future of wireless communication systems. It was a high-level scientific lectures, and we are very pleased with what we heard in this lecture. Based on your achievements in this field, we have felt very honored with your presentation. It was an excellent and very fruitful lecture for all participants, and especially for telecommunication professors and students and all participants. Once again, thank you very much, Professor Jan, for providing this lecture to our faculty. And I want to thank you very much, and Professor Bujar, for the invitation he has made to you. And we will welcome Professor Jan in the next collaboration with our faculty. For then, and thank you very much for all participants for your time.
I can say also a couple of things. I told you in the beginning, Balkan countries have a special place in my heart and also in my life. And I was watching the movie last night by accident, Quo Vadis Aida, and I was crying. And I hope it will never happen again. You need a peace, love for each other. That's why we have this Balkan Camp. And I hope I see many of you in Balkan Camp. Hopefully this year we are trying everything to organize it in Novi Sad. I hope to see you there. And I was in Kosovo myself in 2013. I was in love with Prizren. I really felt like I was in Turkey because everybody was speaking Turkish, but a different Ottoman Turkish, I really loved it. I don't know if we have people from Prizren there. It was a small, beautiful village. There's a nice creek. And I really, it's incredible memory in my life. And then I came to Prishtina and I stayed a couple of days there. So I'm hoping to come back to Kosovo. And it's a really beautiful area, right? With all the beautiful people in the entire Balkan region, food and culture, everything is fantastic, really. So thank you again for listening to me. If you need anything, please let me know. So all the way.
Welcome, Professor, in our university, and we'll go together in prison, to visit prison.
Yes, I hope so. I hope so.
Together to collaborate and cooperation.
We can have a nice lunch or dinner at the creek, these nice restaurants, right? So, yes. Okay, thank you. All the best, and enjoy the evening, guys.
Thank you very much, Professor. All the best.
If you need anything, please let me know.
Thank you.
Thank you very much, Professor, and all the participants.
Thank you. Bye.
Thank you, Professor Bujar.
Thank you. Bye.
Bye. Thank you.